class we were talking about various glass forming criteria. We talked about the criteria based on the phase diagram, and we also talked about the criteria based on what is called the Tg and Tx, for example Trg and delta Tx, and we tried to look at how we classify glasses into bulk glasses and conventional glasses based on these two criteria. One is called the Trg, which is Tg by Tm, and another is the delta Tx. So if you look at these two plots, basically what you see is that as the Tg by Tm increases beyond a particular value of about 0.6, the Rc, which is the critical cooling rate, becomes so low of the order of around 10 to the power 2 Kelvin per second, that means about 100 Kelvin per second, which is something which is easily achievable by conventional casting routes. For example, if you use a normal chill casting or casting in a water cooled copper mold, what you achieve is of the order of around 100 Kelvin per second. So that is the kind of cooling which one can easily achieve without really going into any rapid solidification processing techniques. So these are conventional casting techniques. So just by conventional casting one can achieve glasses, and which is what we define them as the bulk glasses. So all those glasses which can be achieved using the conventional casting techniques are those which are bulk glasses. So in this particular aspect, the Tg by Tm, which is called the reduced glass transition temperature Trg, if one can have more than about 0.6, we can say these are bulk metallic glasses. Similarly, coming to about delta Tx again, if you have a delta Tx beyond about 60 degrees Kelvin or 70 degrees, you can again see there is an inverse relation between the delta Tx and the and the Rc. So as you increase the delta Tx, which is nothing but the Tx minus Tg, the region where the supercooled liquid is stable, we talked about it in the last class, which is called the supercooled liquid regime. So if the supercooled liquid regime is large, we can say the glass formation is more easy, or the glass is more stable. So the glass, whatever glass it has formed, it does not crystallize up to high temperatures. That means the glass is more stable. So such stability of the glass can be correlated to the Rc again, and you can see if you have about 60 or more than 60 delta Tx, the Rc will be less than about 10 to the power 2 Kelvin per second. So again you can call those things as bulk glasses. So bulk glasses are those where the Trg is about beyond 0.6 and delta Tx is about beyond 60. But as I mentioned to you in the last class, these are the empirical criteria based on a large number of experiments on a large number of systems. You can see here itself about 20 different compositions have been put down here. So based on various experiments that people have carried out on a number of alloys, they have found out for each alloy what is the Rc, for each alloy what is the delta Tx by measuring the Tg and Tx, and finally found out this kind of empirical criteria. So these are not really predictive type of criteria. It cannot tell you that before doing an experiment whether a glass is a good bulk metallic glass or not, but only after doing an experiment one can find out whether it is a good glass former or not. But at the same time these are also useful because one need not have to really cast it into the form of a normal casting and for finding out whether it is a bulk glass former or not. What one can do is make an alloy, subject it to melt spinning, which is one of the rapid solidification techniques, and once you subject it to melt spinning you get a ribbon, and take that ribbon and subject it to a DSC, and if you heat it in a DSC you will get the Tg and Tx very easily, and from the delta Tx or Tg by Tm. How do you get the Tm? You heat the same alloy up to its melting point in a DTA or in DSC. If you can heat it up to the melting point, you can find out the melting point also, and once you know the Tg, once you know the melting point, Tg by Tm can be found out. So from such a thing one can find out if it is very large, we can say this alloy is a bulk glass former. So now if I take that composition and cast it by the normal casting route, I can get a good glass former. And this plot also gives you an idea of what is the relation between Tg by Tm and delta Tx with the Tmax, which is what is the maximum thickness one can achieve as an amorphous phase. This is what I told you, it has some correlation to what we say the critical diameter for a hardenability. So whenever we are saying that a particular alloy is more hardenable than another alloy, we always talk in terms of the critical diameter. If an alloy has a large critical diameter, we say it is more hardenable. So similarly here, if the delta Tx is very large, then you can see the Tmax is also very large. So as a result, for all those alloys where for example, you take the case of delta Tx being 100. If you take that 100, so that Tmax is of the order of around, this is a logarithmic scale. So you should see that this is not a linear scale, 1, 10, 100. So you can get about 30 millimeters without any problem. So if you go to about 120 or so, it would be around 130, 140 like that. About 30, 40 millimeters. So one can achieve large thicknesses if we have large delta Tx. Similarly, if you have a large TRG, again one can achieve large Tx. So this can give you an idea that once I measure the delta Tx, put that delta Tx in a plot like this, put that point on that line, and from that line you can measure what is the Tmax that you can achieve for that new alloy. And take that new alloy, now melt it and cast it, and you may be able to get, in principle, because these are all empirical relations, there can be a few exceptions, but otherwise in general one can say that if you take that alloy, you will be able to achieve that much Tmax. That means up to that thickness one can easily get an amorphous phase without getting any crystalline phase. So this is something one can do it. So though these criteria are not really predictive type of criteria, that means they cannot predict whether an alloy is a good glass former or not without making the alloy first, but at the same time they are helpful to make bulk glasses. Whether an alloy can really become a bulk glass or not, we can get an idea from this. And there are also, as I was mentioning in the last class, there are also thermodynamic criteria which are available now. One can calculate what are called the free energy of an amorphous phase, and if the free energy of the amorphous phase is highly negative, we can say the amorphous phase is more stable. So in all those systems, if you take any binary system or a ternary system or a quaternary system, for any given composition, if you can calculate what is the free energy of the liquid at any temperature, let's say consider any temperature such as the eutectic temperature, at the eutectic temperature for that particular system, or at the room temperature, if you do not know where is the eutectic for that particular system, you can calculate it at room temperature. At the room temperature, if you can calculate and find out that the free energy of the liquid is highly negative, then you can say that liquid is a more stable liquid when you compare with some other liquid which has a low negative enthalpy of mixing, or even a positive enthalpy of mixing, or a positive free energy of mixing. Because it's possible that in cases where you have immiscible systems, the free energy of mixing will be positive. We have talked about it in the thermodynamics class. So that if you have delta H mixing being highly positive, even if you add T delta S mixing to it, it will not really make it completely negative. So usually at some compositions you see that free energy of mixing will be positive. So it's possible in some systems it is possible positive, and in all those systems it is almost next to impossible to get a glass. If you want a glass, the liquid should be stable first. Single phase liquid should be stable, and that is possible only when the delta H mixing is highly negative. So if one can calculate the delta H mixing and in turn the delta S add the T delta S mixing to it and get what is called the delta G mixing for that particular phase, liquid phase, and find out that it is highly negative, and one can say that without even making an alloy, that it is easy to predict that this alloy would probably become a glass, and one can make such an alloy in a system, in a ternary system or a quaternary system, identify all those compositions which have highly negative enthalpy of mixing, and you can make only those few compositions and then check whether they become easy glass formers, and in most cases they would become easy glass formers. So these are some of the predictive kind of criteria, and there are a number of people in the world who are trying to make this kind of predictive criteria. Otherwise the existing criteria are these. And we talked about what is the effect of multi-component system on the glass forming ability. We told you that one of the criterion is what is called confusion principle. That means you are confusing the liquid, okay, as far as what kind of a crystal it should take when you add a large number of elements. When you put 5 or 6 elements into the liquid, then all these elements have to rearrange themselves into the form of one crystal structure when a liquid has to crystallize into a crystal, and the diffusivity of all these elements have to come into picture, and as a result you may end up in a amorphous phase instead of getting a crystal whenever you have a large number of elements. That's what is shown by this particular two plots. One is a simple ternary system, zirconium, aluminum, nickel system, and another is a 6 component system, zirconium, aluminum, copper, cobalt, nickel, copper kind of a system, and you can see the delta Tx, maximum delta Tx here is only 70, whereas the maximum delta Tx here is 120. What is plotted here is that iso delta Tx plots. All those compositions having the same delta Tx are plotted here as one line, and if you look at all these lines, finally you can come to one small domain which gives you all those compositions which have a delta Tx of 120, and you can compare that with this which is only about 70. So 70 is the highest in this system, and the highest in this 6 component system is about 120. So from that one can say that this is a better glass former, this 6 component system is a better glass former, and at the same time one can have a large Tmax, what is called the maximum thickness for the glass formation would be much higher in this case when compared to this. So this is one possible way of finding out whether you have a easy glass formers or not. And one more important point to remember is that we use two criteria, TRG, which is Tg by Tm, and delta Tx. What is important to note is that both these criteria are quite synonymous. You can see from this figure that this is a particular system, palladium, nickel, copper, phosphorus, and what we are plotting is the two parameters delta Tx and TRG as a function of copper content. If we keep on varying the copper content, both TRG and delta Tx are varying. But what is interesting to note is that wherever the TRG goes, this is the bottom curve is for the delta Tx, the top curve is for the TRG. Wherever the delta Tx goes to a minimum, the TRG also goes to a minimum. Wherever this goes to a maximum, that also goes to a maximum. So any one of these parameters is more or less a good parameter. And recently a new parameter has been found out in 2002, which is called the gamma parameter, which is nothing but Tx by Tg plus TL. This is by two persons, Lu and Liu. In 2002 this has been proposed, and this is when the people try to plot the RC as a function of this gamma parameter instead of TRG or delta Tx, you get a much better plot. That means all the points can be fitted into a better least square fit line rather than the other. Whenever you fit points in a two-dimensional map, what is important is what is called the correlation factor. Okay, how good is the correlation? Is it 0.9? People say if it is 0.95, 0.99, then we say it's a better fit. If it is much lower value, then we say it's not a better fit. For example, if you are plotting some y with x and you have points like this and you draw a straight line, obviously it's not a good fit. But if you have some y dash with some other x dash and you have all the points like this and then you join a line where all the points fit onto the line, then we say it's a better fit. So people have found that this parameter is much better, and in fact from our own research we found out another parameter which we call it as a delta parameter, which is nothing but Tx by Tg plus Tg by TL. Is nothing but just playing with the parameters, and we found that this gives you much better fit than any of the parameters that have been reported so far, and the correlation factor for this is of the order of 0.95, and whereas for this gamma you get about 0.9, and for the TRG many times you don't get beyond about 0.6 or 0.7. The R parameter, which people usually refer to as which is the correlation factor. So like that one can, how do we do this? What we do is we choose a number of data that is available already in the literature for various alloys, and then try to find out what is the RC for all these alloys, 40, 50, 60 alloys, whatever is available, and plot that RC as a function of this parameter for that particular alloy. And if you try to plot for all these alloys and try to see which kind of parameter gives you the best fit, and with that parameter we can say yes, it is better. The advantage of finding out a better parameter is because in future what you need to know is just to find out what is that gamma parameter or a delta parameter or some x parameter for that particular new alloy, any new alloy that you are making. And once you know what is that parameter for that new alloy, from that parameter you can find out, if you know this parameter, you can find out what is this, that whether it is RC or Tmax, one can find out very easily. And once you know that this is the RC, this is the Tmax, one can easily make a bulk metallic glass of that particular thickness without trying various thicknesses and trying to look at which thickness will give me glass or which thickness does not give me glass. So without going into a number of experiments for that particular alloy, one can just read from such a plot but for that your plot should be a reliable plot. That means the correlation factor for that particular plot should be as high as possible, so that that particular parameter which represents the glass forming ability of various alloys can be a reliable parameter. So what we need is a reliable glass forming criterion, and people, whole of the world, people are struggling for finding out such a reliable parameter, and still a lot of research. This is something which we have just found out about 2-3 months back. Okay, and so there is a lot of work going on in this particular field. The other parameter is what is called the radius. You all know from the Hume-Rothery rules that if you have the size factor which is very small, what is the size factor? What is size factor? Tell me. What is size factor? Okay. So atomic size difference between the solute and solvent atom, is that the size factor? Yes. So that is what we call delta, which is R solvent minus R solute divided by the R solvent, the mod of it. Obviously, because solvent can and solute, solute can be bigger or smaller, we do not know. So always this is expressed in terms of percentage. Multiply it with 100, you will get some percentage, and that's what is we call the size factor delta. So it is this size factor. If it is much smaller, we get a solid solution. That's what we say. And if the size factor is larger than about 12% or 15%, which is again I can say is a thumb rule, which is an empirical rule, and people have found that one can easily get a glass. And now people differentiate the conventional glasses, which are the binary glasses which people have found long back, like such as gold silicon, which is the first glass that people have found, and the bulk metallic glasses, which are multi-component systems, where people see that you need at least 3 elements in a bulk metallic glass, where one element is much bigger, another element is very small, which is very close to being an interstitial element in that big atom, and the third element should be somewhere which is in the middle of these two, so that you have a big atom lattice, which is a solvent lattice, into which you are putting very small atoms which try to occupy the interstitial positions or occupy in the substitutional positions, but by that they create a lot of voids, and then wherein the medium size atom goes and sits and then gives you the best packing possible. If you want to get a good glass, what people say nowadays is that you should make the packing as efficient as possible. The atomic packing, what is called dense random packing, this is called. So if you can make the dense random packing as high packing as possible, then one can achieve a good glass. So that's why what people are doing is, you can see here there are various types of glasses people have found, but one of them is lanthanum based, zirconium based, magnesium based, iron based, if you can look at all of them which are shown here as bars, what you are choosing is, for example, let us take one of the example, lanthanum aluminum transition metal, or anyone, for example, zirconium aluminum transition metal. Where is zirconium? Zirconium is somewhere here, okay, which is you can see triangles. Where is the triangles? Here. So zirconium is here, the aluminum is here. Where is the aluminum? Aluminum is in the middle, and then the other transition metals such as copper, nickel, which is much smaller. So you have a small atom of which is nickel, and then big atom which is zirconium, and aluminum which is in the middle. So if you choose such a structure with a very small atom which is about 1 angstrom is the atomic size of nickel, whereas zirconium is close to about 2 angstroms or bigger than that, and then put aluminum which is in the middle of that, you can get a good glass. So a number of people are trying again empirically with this kind of playing with the atomic radii as one of the parameter. So this is another parameter which people are working on. The next question is, why do you want to go for these glasses, which are particularly the bulk metallic glasses? The major interest in glasses has come nowadays only because of these bulk glasses. Otherwise, people have made glasses in 1959, as I told you, Paul Dubé has made it, and for few years people have been very excited, particularly because of some special magnetic magnetic glasses which are iron, silicon, boron type of glasses. You know, iron silicon is a very important alloy. What for we use iron silicon? Transformer cores. All the sheets in the transformer core, they are all made of iron silicon, because it is a soft magnetic material and its hysteresis loop is very thin. And when people try to make iron boron or iron silicon boron glass, they found that this alloy has much smaller hysteresis loop or much smaller losses than the conventional iron silicon alloy, and much higher permeability. Okay, that means the magnetization is much higher and the losses are much lower. So it's a kind of an ideal ferromagnetic soft magnetic glass, soft magnetic material. So and then people started making these glasses. In fact, there is a company in US called Allied Signal which have been making these iron based glasses of the order of around 10 centimeter width and continuous ribbons like that. You can say strips or ribbons, whatever it is, about 10 centimeter width and kilometers of just by using a typical melt spinning technique. So they take a continuous liquid which keeps on falling on a rotating copper wheel and then keep on collecting that ribbons in like a cold rolling mill. You keep wheel at the end and keep on taking this ribbon which comes out and then just winding it onto the wheel. So like that, people have made a number of compositions like that and cut that at an appropriate position to whatever appropriate size that you want and then put it into the transformer. So that was the initial studies. I think 70s and 80s people have really worked hard on that, but then realized that beyond that they could not really go and use them for structural applications, basically because the glasses for magnetic application, particularly that particular application which is a transformer core, you need only sheets. You don't need anything beyond that. You need thin sheets, and this melt spinner can easily supply such sheets. But if you really want a bulk alloy for any structural application, we want bulk materials. People try to still compact those sheets and make it bulk, but still it is very difficult to avoid any complete bonding between these sheets. So always you will have some interface left out, and that can act as a nucleating site for the crack to nucleate. So people were not really successful to make bulk alloys from that. But when these new compositions have come up, particularly with this confusion principle, when people started putting in so many alloying elements and then started making bulk glasses, that's when people are able to measure the tensile properties. There, if you have a ribbon, you cannot really measure a tensile property. Okay, you can still take the ribbon, put it in a UTM, but unfortunately most of the conventional UTMs, they cannot take a ribbon, melt spun ribbon of the order of around 20 to 30 micron thickness. It's very difficult to test it by tensile test. In fact, we are struggling. Recently we purchased an equipment called Hounsfield tensometer. You must have heard of this. It's a small portable kind of tensometer, which is a horizontal tensometer, whereas typical UTM is always a vertical tensometer. And here we can vary various grips to hold the sample, and we are just about to get a holder which can hold these ribbons, that you make melt spun ribbons. Particularly we are interested to go for the shape memory alloys, where we want to make these ribbons, shape memory ribbons, and then study their mechanical properties. So people are unable to really make tensile properties of them. One can do hardness and get the hardness of these ribbons, but nothing beyond that. One cannot do any compressive testing, one cannot do tensile testing, one cannot do fatigue unless you have bulk samples. So the moment people started getting bulk samples, they were able to measure the strengths, they were able to measure the elastic moduli, and now they know from this that many of the glassy alloys have much better advantage when compared to conventional alloys or conventional materials such as polymers. If you look at polymers, their strength levels are very low. They have very high elastic limit, but their strength is much lower. And you take silica, okay, its elastic limit is also low, the strength is also low, they are brittle. And you look at steels, there are wide range of steels available from low carbons to high carbon steels, but still their elastic limit is much lower, their Young's modulus is not too high. Though people are trying to put as much as alloying elements into it, and new type of alloy design criteria, nowadays we talk of interstitial free steels, automobile steels with high strength, HSLA, high strength low alloy steels. So all kinds of studies are going on in this, how to increase the strength of them, at the same time increase the elastic modulus of them. Whereas in the glassy alloys, if you look at them, you can have a good combination of both strength and elastic moduli. So because of which one can really go for these bulk glasses. Look at another property. One is what is called the resilience, which is nothing but the area under the elastic limit. So you look at the titanium based crystalline alloy, which has some amount of ductility, and but under the elastic domain, if you look at the resilience, it's very small. Whereas the zirconium based glassy alloy, though it does not have high ductility, the plastic zone does not exist much, but its resilience is very large, and because of which people have started using them already in golf club. The golf stick, the head of the golf stick, needs a lot of what is called damping capacity. It should have a lot of shock absorbing. So that is what you can achieve with this kind of thing. So already people started using these zirconium based bulk glasses into that. So you can really make a bulk glass and put it there. So this is one application. Another thing is, again, you look at the strength and the modulus, and if you look at the conventional alloys, if you put all those alloys including super high strength steels, stainless steels, and duraluminum, titanium based alloys, all of them, if you plot strength versus modulus, they all have a low slope. They all fit into a straight line, but that straight line will have a much lower slope when compared to any of the glasses. Here all kinds of glasses have been put: magnesium based bulk glasses, palladium based bulk glasses, zirconium based bulk glasses, nickel based, iron based, and iron boron based bulk glasses. All kind of bulk glasses have been put, and you can have much steeper slope. That means you can have a good combination of strength and Young's modulus in these cases. So that is one of the reasons why people want to go for all these glasses. And finally, one more point I should say is that not only that you can make a good bulk metallic glass, that you can also crystallize this glass into nanocrystals. That's the basic direction in which the whole world is moving now, that people do not want to just make a glass, because glass has its own disadvantages. As I have showed you in zirconium based glass, it does not have good ductility. People want to have some ductility in any alloy. If an alloy is brittle, however strength it has, ceramics for example, they are all very strong, but they are brittle. We don't use a ceramic for any typical structural application. Any structural application should have good formability. So as a result, how to introduce some amount of formability into it, that's where people have realized that if you can introduce some nanocrystallinity into it, that means take a glass, crystallize it under certain conditions so that you can induce nanocrystals into them, and such an alloy you can compare here. For example, this is a glass, zirconium based glass, and as cast glass is just brittle. It has high strength, about you can see 1.6 gigapascals is the strength of it, which is much higher than a steel. Steel is about 500 megapascal, 600 megapascal, nothing more than that. Aluminum alloy is about hardly 300 megapascals. So one can achieve much higher strength, 1.6, but its ductility is poor. There is no plastic deformation. But by introducing some nanocrystals by heat treatment, one can introduce some ductility into this, at least 3%, 4% like that. And people are still trying more and more how to increase this. And one more thing is that by introducing such nanocrystals, by increasing the volume fraction of those nanocrystals, one can increase the Young's modulus, one can increase the hardness, one can increase the fracture strength, and also finally the ductility also. So there are advantages of introducing such nanocrystals into it. So this is another direction in which people are going. How is it done? Simply you make a bulk glass and heat it. You know that glass you can do in a DSE, find out what is the TG, what is the TX. You know the TG, you know the TX. And if you know that if you go beyond TX, it will crystallize. But then the rate of crystallization depends on the temperature and the time, particularly the temperature. So as a result, if you can control the temperature of your heat treatment or the annealing, for example, we know cold working and annealing, we do it to control the grain size. One can control the grain size by just proper choice of the temperature. So if you play around the recrystallization temperature, do not heat much beyond the recrystallization temperature, you can produce fine grain material. Similarly here, you don't go to much higher temperature where the crystals grow to much bigger size, and then once they grow, you lose a lot of advantage of having a nanocrystalline material. So you can control. Yes, this again depends on the type of nucleation kinetics. If the nucleation kinetics are very high, then what you achieve is the whole alloy, this whole glass would have a large number of nuclei, 5 nuclei form, and they grow, and more or less it is possible that the whole glass would convert into a nanocrystal. But it all again depends on a number of parameters. For example, whether what is called a primary crystallization or polymorphous crystallization. What is a primary crystallization? What is a polymorphous crystallization? For example, if you take a glass, let's take, this is the free energy of a glass. If you have an intermetallic compound in the system which has a much lower free energy, and if this is the alloy composition with which you are starting, if you hold this alloy glass at high temperature, the glass has a tendency to form a crystal, isn't it? There is a driving force, and because of this driving force, the glass would tend to become the crystal. And if the driving force is much larger, then the activation barrier will be lower, the nucleation rate will be higher. So there is a possibility that the glass having this composition can transform to the crystal having the same composition. This is similar to polymorphous crystallization of a liquid, isn't it? We talked about polymorphous solidification, liquid having a certain composition transforming to solid of the same composition. If this is happening, then what you see is that if you take a glass, and this glass can undergo nucleation, and a number of nuclei of this particular intermetallic compound having the same composition as that of the amorphous phase can nucleate everywhere in this, and then they start growing, and when they meet each other they stop, so you will get a fine nuclei of this. So complete conversion of the amorphous phase to a complete nanocrystalline alloy to give you what is called a bulk nanocrystalline alloy. Bulk metallic glass giving you a bulk nanocrystalline alloy is possible if you have a polymorphous solidification, polymorphous crystallization. But instead, if there is no intermetallic compound in that system which can form easily, or whose activation barrier for formation is low, instead what would happen is the glass of this composition would try to transform to a solid solution first, having an alpha solid solution.
So, if you start this alloy, for example, if I draw a common tangent, if I am starting from an alloy composition of this, the glass composition of this, instead of this composition number 1, I am starting, let us say, from composition number 2. Now, the glass of this composition number 2 can either form this alpha or form this what is called the intermetallic by what is if you draw a tangent between the glass and the intermetallic, this is the tangent. Yeah, by chance, let us say if even if it is there and but at its activation barrier for its formation is high, then in such a case, even though there is a driving force for the glass to transform to a intermetallic, but its composition, the glass composition is not same as that of the intermetallic. If the composition of the glass is not same as that of the intermetallic composition, what will happen? What you will see is that after the nucleation of the intermetallic, if at all intermetallic nucleates or the alpha nucleates, if this is the liquid or glass, whatever you want to call it, and intermetallic has formed, you have to have some amorphous phase left out in order to maintain what is called the mass balance. Let us say the intermetallic compound, let us say AB kind of a system you have, the intermetallic is a A50 B50 kind of a composition, and you are starting your alloy composition, glass composition is A80 B20. From this A80 B20, it is impossible to get 100% of intermetallic compound having a A50 B50, isn't it? So, as a result, you will always have some fraction of the intermetallic and multiplied by its composition of the intermetallic plus some fraction of the amorphous phase will be left out, multiplied by its composition given by the equilibrium composition given by the common tangent. Once an intermetallic comes out, you will see that the composition of the amorphous phase shifts, because there has to be a common tangent between the amorphous and the intermetallic. So, the composition of the amorphous phase shifts to this point now, and now that is the composition of the amorphous phase. This should be equivalent to what? From the mass balance? Should be equivalent to the glass composition of the glass, original composition of the glass, which is nothing but A80 B20. That is what is lever rule, that is what is mass balance. So, the composition of the intermetallic multiply the volume fraction of the intermetallic. Let us say if I am talking in terms of B atoms, some B atoms are there in the intermetallic, some B atoms are there in the amorphous phase. So, the fraction of the intermetallic multiplied by the number of B atoms per mole of that intermetallic plus the fraction of the amorphous phase multiplied by the number of B atoms per mole of the amorphous phase. If you add this, that should give you the total number of B atoms which are there from the starting glass. Otherwise, you are creating some atoms, you cannot create it. Okay, there has to be the law of conservation of mass has to be maintained, the first law of thermodynamics has to be maintained. So, if you do that way, you can see you will always get what is called a mixture of amorphous phase plus intermetallic compound. This is what is called primary crystallization, not a polymorphous crystallization. If polymorphous crystallization means what? The glass composition is same as the intermetallic composition or the product phase that is coming out. So, the composition of the product phase, if it is same as that of the starting phase, then we can say it is a polymorphous, and then you may end up in 100%. Otherwise, you will always have a composite. This is what we call it nanocomposites, that you have an amorphous nanocrystal composite. And you can have better properties of both that of the nanocrystals and that of the amorphous phase, and you can have the advantage of both. That is why we make composites. You want to have the advantage of the ductile material and also the advantage of the brittle material, so that you can have a good combination. And yes, but yes, this is another thing. Whenever you make them in the nanocrystalline form, then the brittleness which is coming is basically because of the intergranular cracking. So, here you have nanoparticles embedded in an amorphous matrix. So as a result, you don't have brittle complete grain boundaries in that. It's not a polycrystalline material. So as a result, the crack does not go through the grain boundaries. So as a result, you can have some kind of arrest of these cracks, so the crack do not propagate. So that is one of the advantage of making these nanoparticles in embedded in an amorphous matrix. So one can have additional advantage of good fracture toughness in these materials. People have shown in a number of materials that even by putting these intermetallics in a nano form, for example, we have seen ourselves that you have an aluminum matrix with a intermetallics of Al3Ta, you can have much better fracture toughness, provided their morphology is controlled. We will talk when we talk about titanium based alloys. It all depends on the morphology of the second phase particles, and one can control the fracture toughness just by changing the morphology of the second phase particles. Okay, we will talk about this. So this is basically about the formation of the composites from the bulk metallic glasses. But coming to the bulk metallic glasses itself, under what condition a bulk metallic glass can form? People have thought of basically three criterion. One is a multi-component system, that it should be a multi-component system, otherwise you will not get a bulk glass. Second is that it should have a significant atomic size difference, the size factor should be large. And third, it should have a large negative heat of mixing. This is what I told you from the beginning itself, that if the liquid has a large negative enthalpy of mixing, then it is more stable, and if it is stable, then the glass is stable. If the liquid is stable, glass is stable. Glass is nothing but liquid. Nothing but liquid, is only in a solid form, configurationally frozen liquid. This is what we say. So based on this, people have given some kind of a route map of how to get a glass, how to get a bulk glass, and this route map is something like this. If you take constitutive elements, that means if you have more than 3 type of elements with atomic size differences more than about 12%, and you have a large negative enthalpy of mixing, if you choose such system, what you do basically is that you increase the degree of dense random packing. So if you increase the dense random packing, you will have a good topological packing, and at the same time chemically also the bonds will be stronger because the delta H mixing is highly negative, and as a result what you end up is that new types of liquid, the liquids with dense random packing, the liquids with good short range order, and such liquids which are multi-component liquids with good short range orders in such a liquid, and those liquids will result in increase in the solid liquid interfacial energy, and if the solid liquid interfacial energy is high, then the formation of crystalline phase is more difficult. When a liquid is giving you a crystal, what is that gives you activation barrier for a crystal to form? It is only the interfacial energy. If the interfacial energy is very low, then the crystal formation is very easy. If we can somehow increase the interfacial energy or the surface energy, then the crystal formation is more difficult. That is why we always say that the liquid to crystal formation is more difficult than the crystal to liquid formation. When I set a liquid crystal and start heating it, I always see a crystal always melts at the melting point. But when I take a liquid and start cooling it, it never solidifies at the melting point. I always have to cool it below the melting point for it to solidify. Why does it happen like that? Because from a liquid, a solid has to nucleate. If a solid has to nucleate, a new surface has to be created. If you want to create a new surface, you need to have certain energy to overcome the surface energy. And how do you get that energy? By undercooling. If you undercool it, you have certain free energy which is available, because we know that free energy, which is the driving force, is directly proportional to the undercooling. So if you have some undercooling, some driving force is there, and that driving force can be used for creating the surface, and that's how you create a surface. And if you don't give that driving force, you can't create a surface. That's why you keep your liquid at the melting point forever. Crystal cannot form unless there is a condition under which it can still form. we add some heterogeneous nucleating sites. If you really add heterogeneous nucleating sites which can provide that surface, you can still have solidification occurring at the melting point without any undercooling, and that is what is heterogeneous nucleation. Whereas if you are doing the reverse process, crystal being heated, you do not need anything because already heterogeneous nucleating sites are there, which is nothing but the surface of the solid. Okay? And that is why I told you before also, when you take an ice cube, always melting starts at the corners because those are the regions of high surface energy, and that is why the number of bonds broken are high there. So the broken bonds is what gives you the high energy. This is what, I do not know if you have ever thought of this. Whenever you take a polycrystalline material, let us say simple aluminum, okay, pure aluminum, polycrystalline aluminum, you cut it, polish it and put it in a and etch it and put it under an optical microscope. What do you see? You see grains and you see grain boundaries. But at the same time, if you carefully observe each grain will have a different gray level. Some grains look bright, some grains look dark. Why is that? We say this is orientation difference. Why should orientation difference really give you this kind of different shades? Have you ever thought about it?
Number of free bonds in the area. Is changing with the.
Do you think that the optical light is interacting with the bonds there? Nothing. It is the etching which is different in different grains. Why the etching is different in different grains? Different planes. If you think of a material with two grains here, grain 1 and grain 2 and grain 3, let us say, you imagine, look at what are the planes which are parallel to this surface. If you look at here, maybe 100 planes are parallel to this surface, and maybe in this particular region 111 planes are parallel to this surface, maybe here 110 planes are parallel to this surface. If you look at 3 different grains, with each one of them, because you are polishing it, you are cutting a surface and polishing it and putting an etchant there, and look at any plane which is parallel to that surface, and if you look at each grain will have a different plane which is parallel to the surface. If they are the same planes, then you do not call it as a different grain. Okay? So we say each grain should have an orientation difference. So if there is an orientation difference, then the orientation is different. So the same plane cannot be parallel in grain 1 and grain 2 for the top surface. Each grain should have a different plane which is parallel to the top surface. If that is the case, now if you put an etchant on this uniformly, and the amount of attack that you have is going to be different in different regions, because each of this region will have a different energy, and that energy depends on the surface energy of that particular region, and that surface energy is different for different planes. For 111 plane, the surface energy will be different. For 110 it will be different. For 100 it will be different for a given crystal. Let us say if it is an FCC crystal like aluminum. In an aluminum, which grain will have, which particular plane will have the highest energy? 111. Why? Close packed. What is the meaning of close packed? Because the number of broken bonds are more per unit area. The number of broken bonds are more. If the number of broken bonds are more per unit area, then it has more surface energy. If the more surface energy, then more attack. Why is the grain boundaries get attacked more easily than the grain? It is just because of the higher surface energy. So that's why you can see that interfacial energy is crucial to suppress the crystallization. Second, similarly, difficulty of atomic arrangement. When you have large number of atoms, all these atoms have to come together to form a unit cell, which is much more difficult. Again, you are making it difficult for the atoms to diffuse. Diffusivity gets restricted, and because of the diffusivity getting restricted, and having higher viscosity, when you put large number of atoms, the viscosity is increasing, because of which you can see there is an increase in the Tg. Okay, glass forms more easily. That means when you are cooling the liquid, the glass can easily form because viscosity is much higher. I have shown you a viscosity plot, okay, viscosity versus temperature plot once in the beginning, okay, and you can see if the Tg is, if the viscosity of a liquid is much higher, then the glass formation is achieved much easily. So as a result, that is one. And similarly, in case of crystallization, you have a necessity for atomic rearrangement on a long scale. Okay, you need long range atomic arrangement for a crystallization, and that is more difficult with the diffusivity, and because of which you can suppress the growth of a crystal. Not only crystal nucleation is difficult because of the atomic rearrangement is difficult, and because you need a long range arrangement for making the crystal to grow, and that is again difficult because of the diffusivity being low. All these things will lead to a decrease in the melting point and an increase in the Tg by Tm, and that's what will give you a good glass. And so this is the based on this, people have seen there are a number of systems where people have got these glasses, and I just quickly give you some classification of these glasses. They are basically classified into 5 groups. One is a early transition metal, late transition metal, and aluminum type of group number 1. And the group number 2 is early transition metal, late transition metal, metalloid. For example, zirconium, aluminum, nickel, zirconium, aluminum, copper. This is an examples of group 1. Iron, zirconium, boron. These iron is a late transition metal, zirconium is a early transition metal, boron is a metalloid. So that is the group 2. And group 3 is late transition metal, aluminum, metalloid type of thing. Iron, aluminum, metalloid kind of examples. Group 4 is another, which is early transition metal, late transition metal, and magnesium type of alloys. And group 5 is the late transition metal and metalloid, which is the simple palladium nickel phosphorus, palladium copper nickel phosphorus. So a number of such alloys have been made, and people have found good glass formers in all these. And if you look at how the whole field has evolved, starting from the simple gold silicon system in 1959 with 20 to 50 microns, and now we see we have palladium nickel copper phosphorus with about 72 millimeters. This is about I think a slightly old news. Now very recently people have even found out about 100 millimeters, and so you can see that a number of non-ferrous systems, ferrous systems. It is not that this is restricted to one type of systems only, all kinds of systems, okay, wherever all those criteria which I have mentioned before are satisfied, one can get a glass. We'll stop here, and in the next class we will talk about quasicrystals. Thank you.